Welcome to Chapter 8, Climate and Climate Change with Biomes. So with this chapter, what I plan to do is talk about general concepts of climate, talk about climate change, and then weave in concepts of biomes or areas that have similar vegetation. Now, one thing that we can talk about first, which bridges concepts from Chapter 7, is Trans Nino and its connection to tornadoes. Recent research has shown that when an El Nino phase is ramping up or a La Nina phase is going away, we can observe greater tornado frequency in the Midwestern part of the United States. This was very evident back in 2011, especially during some of the major EF5 tornadoes that occurred in May and June within the United States. Terms for this chapter will revisit weather and its distinction between climate. We are going to look at the difference between weather and climate. Then we're going to look at insolation once again in connection to biomes, and biomes in connection to deciduous trees and mesothermal climates. Chaparral, similar to deciduous trees, are certain types of biomes that are closely connected to climate. Then we will look at climate change and some of the issues that we've seen with climate change, both natural and human-induced, in addition to some tools that we have to understand what climate is doing now and what it might do in the future. One question I ask my students is, where do you think this picture was taken? I've done that before, and this is a fun one. So take a second to think if you can figure out where this picture was taken. One clue is there is a very long lake, and in this lake, a famous pseudo-monster called the Loch Ness has been presumably sighted here. But the question I ask students is, what do you think the weather is right here, right now, while this picture was taken? A lot of students say that it looks like a nice sunny day. But if you know where this was, if you know where this was taken, which was in Scotland, you know that the general weather pattern there is cloudy and rainy. That's why there's so much green vegetation here. So that brings us to the difference between weather and climate. Weather is the short-term conditions of the atmosphere, the day-to-day conditions. You know, you may have a rainy day, a cloudy day, a sunny day. But climate is the long-term condition, how the weather behaves over a long period of time. And this includes averages of certain variables, such as rain and temperature. But it also includes the extremes, record highs, record lows. And by the way, the minimum length to determine climate is 30 years. So in this chapter, we're going to just look at some climate classifications and then talk more about climate change. So exactly what is climate and what is it composed of? Essentially, climate is very complex. And one of the variables, probably the most important variables, is insolation, incoming solar radiation. That's linked to temperature. And if we go back to Chapter 4, looking at the primary temperature controls, insolation is number 1. It's connected to temperature and connected to latitude. We also look at other variables very common in meteorology, which are also common in climate studies, with one major exception. Day-to-day weather isn't necessarily concerned with greenhouse gases, but over the long period, we definitely need to look into this. There are millions of variables, so this is a short list, and in order to understand the complexity a little bit and its interaction with the Earth and all of the Earth's physical systems, we need to take a look at this slide in more detail. So this is showing you, or hopefully giving you, an appreciation of how complex and interactive climate really is. We have atmospheric and ice connections, ice and ocean, atmospheric and land, atmospheric and ocean. Atmospheric and ocean, by the way, is one of the most teleconnected, which is a term that we use when we connect two different physical systems of the Earth. It's one of the most highly researched phenomena out there, and it's really what El Nino is. El Nino is an interaction between the atmosphere and the ocean. So we have some of the major spheres of the Earth: atmosphere, hydrosphere, biosphere, lithosphere. The cryosphere is just the ice portion of the hydrosphere. And it also interacts with radiation that leaves the Earth and comes from the Earth, or from the sun actually. So again, very complex. So when it comes to greenhouse gases that we look into and modeling climate in the future, it takes very powerful computers. Now, to keep things a bit simple, we're just going to focus on, for now, temperature and precipitation. These two variables can do a pretty good job depicting climate. It also helps us understand biomes, biomes are areas on Earth closely connected to its climate that have very similar vegetation within that area. So let's go to some extremes here. We're looking at this cartoon, this diagram, and we have lush vegetation. We look at tropical rainforest. We have so much vegetation sometimes that when you get to the bottom of a rainforest, only 3% of the sunlight makes it to the bottom here. So these are in conditions where it's very wet and very warm. On the flip side, when you have areas that are very cold and very dry, you barely have any vegetation growing. And we have tundra. And this is an example of tundra in East Greenland. Somewhere in the middle, you might have an average amount of precipitation, and your temperatures are average or somewhere in between the spectrum of very cold and very warm on Earth, and you do get some vegetation. On the wetter side, you would have deciduous trees, such as these here near Chicago. On the drier side, you may get cactus and other things you see in a much more humid desert climate, such as the Sonora Desert in the southwest United States. Other biomes you may be familiar with would be needle-leaf forests, common in the mountains or as you go farther up or farther north in latitude. So these are just some examples of biomes. Another way to experience biomes is to put a large mountain near the tropics. One example that I know are some of the volcanoes on the Big Island of Hawaii, where you may be at the very bottom of, let's say, Mauna Kea, and you have tropical rainforests. You go up a little higher where it's colder and you get deciduous forests, then needle-leaf forest, then tundra. Then you get to a point where no tree or any vegetation will grow and you just get ice and snow. About 100 years ago, a climate expert named Köppen classified the world's climate based on temperature, precipitation, and the timing of these two variables. So what this produced is a variety of different types of climates and subclimates. Now, I'm not going to get into all of these climates quite yet. I do get into more of them in Geography 15. But what I do want to focus on in this chapter are mesothermal climates, which really mean warm winter. And specifically, we'll focus on Mediterranean climate, which is what constitutes most of coastal California. So, mesothermal climates include three major climates. Humid subtropical hot summer climates, which are found very prominently in the southeastern United States. Marine west coast climates, found in the Pacific Northwest. And the Mediterranean dry summer climates, which are found in coastal California regions. However, they do exist in other places around the world. Here is a map of mesothermal climates, and it shows you some of the areas around the world. Now let's focus on Mediterranean. Mediterranean obviously gets its name from the type of climate that we see in and around the Mediterranean Sea. We also see this in southern Australia, South Africa, and it's not depicted very well here, but it's also on the coast of Chile and here in California. This map does a better job of showing you where the dry summer Mediterranean climates exist. And so as you can see, there are really just 5 major areas that we have this type of climate. Alright, so let's go back to the first mesothermal climate, humid subtropical hot summer climate, and we're going to look at temperature and precipitation. So we have one city here. This is Columbia, South Carolina. If you just look at precipitation, we have quite a bit of precipitation throughout the year. And in fact, it looks like we have more precipitation in the summer months. One thing that makes this mesothermal is the temperature. The temperatures, although they range quite a bit from winter to summer, average temperatures never make it below freezing. It doesn't mean that this place won't have freezing temperatures. These are just averages. And with all this rain, we have quite a bit of lush jungle, or not really jungles, lush forests and grasslands and trees. Now let's go to Marine West Coast. We're looking now at Vancouver. Vancouver, British Columbia, Canada. Notice something here. The amount of precipitation during the summer has now dropped. And this is very common along the west coast of the United States and along the west coast of South America as well. Even though Vancouver is pretty far north, we're looking at 49 degrees north, average temperatures do not make it below freezing, mainly because they're along water, in areas near water, even at this latitude, don't necessarily get below freezing. Check out the Mediterranean climates. What do you notice now in the summertime? There is very little rain. In fact, so we have 2 cities here, San Francisco, California, and Sevilla, Spain, both at 30 degrees north. Very similar as far as precipitation. Now Sevilla, Spain is a little bit farther inland, so they have warmer temperatures. San Francisco is surrounded by a body of water, so their temperature distribution is muddled. Nonetheless, both cities do not have average temperatures below freezing. And by the way, if you're curious about what Southern California would look like if people didn't plant trees here, at least in the hills, it would be covered by the Mediterranean chaparral. These oily bushes are very, very, depending how you look at it, good for local vegetation, local biome and preservation, but are not good for Santa Ana wind events because they like to ignite if we have fires. So now let's turn our attention to global climate change. We're going to look at global warming, temperatures and carbon dioxide, climate models and future temperatures, and because Antarctica doesn't get mentioned too much in climate studies, I will talk a little bit about Antarctica. So what are some causes of climate change? One of the most historic causes of climate change are volcanoes. Volcanoes, along with asteroid impacts, can actually add ash and soot into the atmosphere and cool the planet down. Humans also can do this. What it does is it increases the albedo of the Earth. Now lately we've been looking at human influences on greenhouse gases, and there's a lot of evidence suggesting that the more greenhouse gases there are, the higher the temperature will be. But we can't just stop there, because the Earth is a complex system. We have to look at something called feedback mechanisms. We are already seeing this in the Arctic areas, because what we're seeing is we're seeing a positive feedback. For example, we know in the Arctic areas we have more warmth. Warmer air temperatures will actually melt more ice. The less ice there is, the lower the albedo, and then the warmer the temperature. Warmer the temperatures, greater sea ice melt, and the cycle goes on and on. However, for water vapor, if we have a warmer planet, we will potentially have more evaporation, but more evaporation could create more clouds, and clouds could cool the planet down. So it's not very simple. We have to look at some of these mechanisms that we've just talked about here in computer models to really understand what's going to happen. Other reasons, other more natural climate change causes include solar output fluctuations. Now, sunspot activity can be related to solar output, but studies have shown that there isn't much, there at least hasn't been much of a change in solar output in the last 300 years or so. Variations in the Earth-Sun relationships definitely cause changes in the climate, but over very long periods of time. So over 100,000 years, the shape of the Earth's orbit will change from a circular to an ellipse back to circular. That can affect some of the warming seasonal periods that we have across the world. The inclination of the Earth actually goes from 24.5 degrees to 22 degrees within a 41,000 year period. This also changes the timing of the seasons. The precession every 26,000 years, instead of pointed toward the North Star in the northern part of the sky, it reaches Vega, or points to Vega, the southern part of the sky. And this precession can affect seasons as well. Now when you add up all of these, you get something called the Milankovitch cycles. And this has definitely impacted Earth in terms of the most recent ice age. So what are some evidence that we have of current global warming? This is quite a graph, and you see it in many different forms. And it essentially shows you that the Earth is warming up, especially since 1980. We have noticed, based on the World Meteorological Organization, that 13 out of the 14 hottest years on record have occurred in the 21st century. Global temperatures are increasing 0.13 degrees per decade. That doesn't sound like a lot, but if you add that up, and knowing that some areas are warming up faster than others, then this could be quite alarming. We have seen sea level rise and expect much greater sea level rise. Temperatures in the Arctic are increasing twice the rate of everywhere else, which is again what I was talking about with the positive feedback mechanisms. And based on coral and ice core research, carbon dioxide is increasing at a faster rate than any other time in the last 800,000 years. So what does this all mean? How or what could possibly occur? About a ½ degree Fahrenheit per decade of warmth, which in some areas could be up to 7 degrees warmer. That again may not seem like a whole lot, but for fragile ecosystems and everything that's relying on us, including humans, that could be quite a bit. Sea level rise, more sea level rise at least. Stronger tropical cyclones, although some studies suggest we may have less. Increased precipitation and increased drought. So again, a lot of these studies are showing extremes. So instead of just saying increased precipitation, increased drought, we could just say we're seeing extremes, which include flooding and drought. Here's another graph showing you the same temperature patterns that I showed you before, this obvious spike since 1980. But one thing I want to put into perspective here is what Mount Pinatubo did to global temperatures. Mount Pinatubo, a major eruption in the Philippines in 1991, cooled down the planet. So again, aerosol activities is one of the things we've got to consider. Now this is showing you the difference between the northern hemisphere and the southern hemisphere. Notice that the northern hemisphere has quite a bit of an increase of warmth. Again, going back to chapter 4, part of this is due to how much land there is in the northern hemisphere. The other aspect is how much industry and other mechanisms that pollute the air and what they can do to increase temperatures. Where is this warming exactly? Well, from 1961 to 2010, we have noticed that most of the warming occurs, like I've already mentioned before, in the Arctic areas. Now remember back in chapter 1 and chapter 2 when I talked about maps having certain projections. It does make this area a little bit bigger than it would be otherwise, but nonetheless the Arctic areas are the areas where we see the most warmth, and also some of the areas in the outer parts of Antarctica. Now this is an interesting slide, so let's take a moment here to look at the date. The date was about 10 years ago. So 10 years ago, they mentioned that in 1995, the countries that are outputting the most carbon dioxide pretty much was the US and other developed countries. China was only 14, and developing countries included only 13. They projected that in 2025, which is now only 9 years away, that China would be 15% and the United States would be 17%. Actually, a few years ago, China has surpassed the US as the number one carbon dioxide emitter. So that presents more challenges as we try to work on climate change and its solutions globally. One of the things that scientists, at least climate scientists, do is they use general circulation models. These are computer models that are housed in government facilities, huge computers, supercomputers again, and they try to model as many variables as possible along every height in the atmosphere, along as many spaces across the Earth as they can. And using physics and math and chemistry, try to model the physical aspects of climate. And so this is what's helping us understand what's happening now and what might happen 50 to 100 years from now. They're not perfect, but it's the best method that we know of so far to understand climate change. And going back to Antarctica, I will be posting some videos, by the way, on biomes, on climate change in Antarctica. But Antarctica, it has a much different climate than the Arctic areas. Remember, the Arctic is over the North Pole. The Antarctic is an actual continent over the South Pole, and in closer to the South Pole we see so much colder temperatures. We see temperatures much colder than the Arctic areas. So it's going to take dramatic climate change to warm those areas up. But along the edges of Antarctica, we are seeing ice disintegration, sea ice melting, and even the land ice, or glaciers. And it's those glaciers that must melt in order for sea levels to rise. So there's a lot of work left to do to understand climate. And one thing I just want you to remember is that climate is very complex. It's multi-dimensional, so it requires feedback mechanisms to understand. And exact mechanisms of what's going to make the climate warmer are not well understood, but the consensus generally is that humans have an impact, and we should at least try to minimize that impact for chances that climate change will not be so drastic.